Hello everyone, I'm Sandip Chakraborty, an Associate Professor at the Computer Science Department of IIT Kharagpur. So in this teaching seminar, I will talk about one interesting component in the computer network course at the transport layer, where a particular metric called bandwidth delay product has significant impact on the design of the transport layer protocol like TCP. So what is bandwidth delay product? The bandwidth delay product, by definition, it is the product of the link bandwidth and the link delay, but it is an important metric for the flow control algorithms that we have already discussed. So as an example, if you consider that the bandwidth is equal to 50 kilobyte per second and the one-way transmit time, say the delay, is 250 millisecond. So your bandwidth delay product or BDP will be 50 into 250 converted to second. So it will come approximately 12.5 kilobit. Now, if you assume that TCP kind of protocol where 100 bit is being used for the segment size, so your BDP is approximately 12.5 segment. So what does BDP signify? So if you think about your network as a pipe, and you want to find out that what is the capacity of that pipe. Think about any kind of water pipe. So the capacity of the water pipe is typically the length and the cross section. If I multiply by it, so we'll get the capacity of that pipe. Now if you try to map it to a network, so in a network, if you think your link bandwidth is actually giving you the cross section of the pipe. That means how much data you are being able to push on your link, just like how much water you are being able to push on the pipe. Similarly, the link delay is equivalent to the length of the pipe. So that way, for a network link, the metric BDP is actually giving you the capacity of the link, or in other way, the amount of data that the link can carry. Now, how does it impact? So if you consider the event of a segment transmission and the corresponding acknowledgement reception, this will take one round trip time. That means it is twice the one-way latency. So that way, if you think about a sender is going to send some data on the channel, then at the other end, your receiver is there to accept that data. Now at any point of time, the maximum number of segments that can be outstanding is equal to twice the BDP. That means equal to 25 segments. That means the sender is continuously pushing the segment, the receiver is going to take the segments out of that pipe, and within that pipe, there can be a maximum of 25 segments, including the acknowledgement, that can remain outstanding. So in your flow control algorithm, the sender side window that we talked earlier can be a maximum of 25 segments. That way these two parameters are interlinked. Now, as I mentioned that this have an implication on the window size. So this maximum number of segments that can be outstanding within this entire duration is actually 25 plus 1 equal to 26, because the acknowledgement is sent only when the first segment is received. So you can think about that the first segment has just been received and the acknowledgement is being transmitted. So you have a total 26 different segments which are outstanding, and this will give you the maximum link utilization. So the link will always be busy in transmitting data segment if you have that many number of segments outstanding in your window. So in mathematical term, if BD denotes the number of frames equivalent to BDP, W is your maximum window size, then W will be equal to 2BD plus 1, which will give you the maximum link utilization. And that way, this is an important concept to decide the window size of the typical window-based flow control mechanism. Now the BDP has also an implication on top of the protocol design choice. So you consider a link bandwidth. The bandwidth is equal to 1 megabit per second and the delay is 1 millisecond. You consider a network where the segment size is 1 kilobyte, that is 1024 byte. Now we have talked about three protocols: stop and wait, go back in, and selective repeat. If I ask you the question that which protocol is better for flow control for this link? So if you compute the BDP, you will see that the BDP is coming to be 1 kilobyte, right? Now your segment size is, the BDP is coming as 1 kilobit. and your segment size is equal to 1 kilobyte. So that way, the segment size is 8 times larger than your BDP. Well, so that means the link on which you are transmitting your data, that link cannot hold the entire segment completely. So even if I use the sliding window based protocol like a stop and wait protocol or a go back and protocol, the sliding window protocol will not improve my performance in this case. So better to go for a simpler protocol like a stop and wait. Your stop and wait protocol has less complexity. So because you are not gaining anything by using a sliding window based protocol in this case, so better to fall back with the simplest protocol, that is stop and wait, which will work good in your network. And indeed, that way you will see that the older Wi-Fi routers, the Wi-Fi technology, when the speed was not that high, today's Wi-Fi is approximately 1 Gbps. I am not talking about the Gbps Wi-Fi, that are the Wi-Fi when the speed was few hundred Mbps maximum. There we used to have this stop and wait protocol at the flow control layer. Well, so that way the BDP has a significant impact on the choice of the protocol that you are taking as a network engineer, and also the design of your protocol. That means how much window size you will use if you are going to apply a sliding window based protocol. So that way BDP gives a very important metric for your network design.